Okay, section 5.1, talking about simple harmonic motion. Number 12, a 20-kilogram mass is attached to a spring. If the frequency of simple harmonic motion is 2 over pi cycles per second, what is the spring constant K? So that's the first thing that we're asked. Let's examine that. And so they tell us that the mass is given to be 20 kilograms. It's attached to a spring. They give us the frequency. The frequency is said to be 1 over the period. And so this is omega over 2 pi, because the period is given to be 2 pi over omega. Okay. So they give us this frequency. So that formula is omega over 2 pi, and the problem says that the frequency is 2 over pi. So from here I want to extract from there omega. So we just cross multiply, and this implies that pi times omega is equal to 4 pi. So that implies that omega is equal to 4. Well, why is that important? Because there's a formula that says omega squared is equal to the spring constant divided by the mass. And the question here, what is the spring constant? K. So I'm asked to find K, so I need to know omega, and I'm given the mass. All right? So we said this implies that omega squared, so that's 4 squared, is equal to the spring constant that we're looking for, K all over M, and M is 20 kilograms. So we get K is equal to 16 times 20. K is equal to 320. And this is kilograms per meter in terms of the so-called spring constant. So K is equal to 320. So that's the first question, right? So then it says, what is the frequency of simple harmonic motion if the original mass is replaced with an 80 kilogram mass? Well, let's draw a line. So we know that we have omega squared is equal to K over M. Now the spring constant is set to be set, so it's going to be 320. Yes, over 80, right? And so we can use that to find omega. Omega is used in the formula for the frequency, right? The frequency is omega over 2 pi. Right? So once we have omega, then basically we also have the frequency. Just take that omega divided by 2 pi, you get the frequency. So here, we say this implies that omega squared is equal to the spring constant, 320. That's over here. The new mass is 80. So here we get 4 omega squared, that is. And so that implies that omega is equal to 2. So if we know that, we have the frequency that we're asked to find now, and that's 1 over the period, or omega over 2 pi. So this is 2 over 2 pi, or just 1 over pi. So the number of cycles that this frequency makes is 1 over pi cycles per second. Okay. So that's all they ask you to find there. Very simple formulas. Any questions there? Let's look at number 13. Here, a mass weighing 24 pounds attached to the end of a spring stretches it 4 inches. Initially, the mass is released from rest from a point 3 inches above the equilibrium position. Find the equation of motion. Let's start at the beginning. It says that a mass, so here this is M, mass is 24 pounds. It's attached to a spring that stretches it, and that stretch is set to be little s, and we just say, just for simplicity, that is x. So here it stretches it a distance x units. We say x is equal to 4 inches. We have to, is that a beatbox, David? Or you're going back to my days, you know, Dougie Fresh, you know, the human beatbox, you know. Hey, that's right. My wife now, I didn't know her when I was growing up. She lives in New York, lived in New York, and her uncle, who lived down where I live, and I had 2 friends that I grew up with. My best friend, Cleophas, and then Rodney, my wife's uncle. We were all in the same class. That I just believed that they were just the best liars in town. They could just really tell some good ones and have you believe in it, you know. And I mean, oh man, yeah, just lied about everything, you know. And I could go into depth, but I won't. But anyway, her uncle Rodney, I could kind of tell that he was lying because the way he talked, you know, it just sounded like he was just lying. And so, yeah, and so he would tell us in school, in high school, that his sister lived right by the Fat Boys. Now, back in my day, the Fat Boys, that was the group, man. You know, Human Beatbox and, you know, Kuroksky, you know, man, those guys, they would put it down. And then, you know, I considered myself a beatboxer, you know, back in junior high school and high school. I'm telling the truth, man. You can write. It was a fella I went to my pastor's funeral Saturday, and one of the deacons, he said, look, he talked about the pastor and talked about the church, and he said, you can write on your paper a T for truth. You can put a T on your paper, my friend, for truth. I was a beatboxer, and my reign of fame lasted for about a year until a guy from New York came down. He could out beatbox me, and so, you know, I never be outdone, so I just quit altogether, you know. So I became the artist formerly known as the one that could do the beatboxing. So I went from beatboxing to trying to be a DJ, but you can't be a DJ with one turntable. But anyway, it just don't work when you just kind of scratch on grandmama's, you know, Capona set. But anyway, man, Rodney said that his sister lived right across the street from the Human Beatbox. And, man, we would say, Rodney, you lying. So I get married to my wife, wasn't thinking, putting everything together. And so we're driving from her parents' house and like maybe 2 or 3 houses. And she says, that house there is the house where you know, it was 3 guys, the Fat Boys. It was the one that did the beatboxing, and it was the light-skinned dude, and it was the dark-skinned dude. This was a dark-skinned dude. I forget his name, whatever. But she said that's where he lives. Or he lived then. I think the parents, probably live there now, whatever. And I said, wow. Rodney was actually telling the truth, man, you know. But, you know, he was like, what's that old story back in the kindergarten? Yeah, the boy that cried wolf. He cried wolf so many times that when he actually told the truth, you just thought he was still Yeah, it's just still lying, you know. I said, man, this guy was really telling the truth. And he would tell us about, he would hang out with LL Cool J and Run DMC and all this stuff, right? Well, here's the thing. My wife, their first house, they moved to Long Island, but their first house was in Queens. And LL Cool J was from Queens, so she took me to Farmers Boulevard, and right there, not too far from their church, is Farmers Boulevard, where LL Cool J grew up. So maybe Rodney was telling the truth, you know, so I don't know. But anyway, oh boy, man, but hey, he was a good liar, though, man. You know, he was good. But anyway, that's crazy stuff. This, I don't know why I got on that. Anyway. Huh? Oh, yeah, the beatbox. Yeah, that's right. Now, and somebody asked me, was I a beatboxer? Man, I could do it, but the stuff that I did, you know, anybody can, you know. You know, all that, you know, man, just making crazy, you know, sounds and stuff, man, you know. Man, it's on it, man. It's on it. Okay. Let's get back to differential equations. And you know I'm so lazy, I don't go back and delete nothing, you know. So all of my old sermons, when I'm fussing, they're still on there, man. That's right. One year they had me preaching on this thing, and you know, you got to go to a black church to really experience some. You know, when the preacher, he ends his sermon, we call it hooping, whatever, you know. You know, his voice changes. So they had me doing some of that stuff, you know, one of these days, a couple years ago. Crazy stuff. Anyway, thank you, David, for that intro log, you know. X is 4 inches. The only problem here is that the dimensions with respect to the force of gravity, which is 32 feet per second square, those units are in feet and not inches. So we have to convert all these inches to feet. And then once you do that, everything matches up. So here we convert the 4 inches times 1 foot per 12 inches. So we get, is that 1/3? Of a foot. So, and we're using that for X. All right. Now, they want us to build this equation for motion, and the main thing that you need initially is the omega squared. We need omega because omega squared is equal to K over M, where, if you recall, we have the mass times the second derivative, which is basically force, and we set that force from Newton's second law with Hooke's law. We said this guy was a restoring force, and if you recall, you put them both together. So we have M times X double prime is equal to negative KX, and this implies that M times X double prime plus KX is equal to 0, and then we divide through by M, so we have X double prime plus K over M times X is equal to 0. We replace K over M with omega squared. So let omega squared equal to K over M. So this implies that x double prime plus omega squared times x equal to 0. When you solve this guy, this implies that the solution is x of t is equal to c sub 1 times cosine omega t plus c sub 2 sine omega t. So the thing that we need is omega, right? Give me omega, and then I can write the equation of motion. And then we have to also solve for C1 and C2, and that comes from those initial conditions, which we'll get to. So if you go back to this problem, so we have a mass weighing 24 pounds. And let me just correct something in my notation here. This mass here is actually a weight. And let me write it as such. So I'm going to put capital W for the weight. So here, the weight. The weight is given in terms of its formula as the mass times the gravity of acceleration. So this implies for this problem we got 24 pounds is equal to the mass times here 32 feet per second squared times mass. Now what do I need? I need the mass, because look at this guy right here. See if I can highlight it. This M I need for the mass. And I need that constant K to be able to build omega or omega squared right here. So what we have is basically that the mass is 24 divided by 32. So So 3/4 of a pound. So I got the mass, and let's see. If you take Hooke's law, which says that you have the force is equal to some constant times x, assuming that the restoring force is inclusive of K. Do you know that the weight itself acts as a force? Weight. So taking weight to also be force. So here I have this F equal to K times X, where the weight here is given to be 24 pounds. That's equal to some constant. Here, the X we have to use is the X that we had translated 1/3 feet. So here we get K is 24 times 3. And this is basically pounds per feet. So K is 72 pounds per feet. So I got K, and I have M, the mass. And so now we can build this omega squared, which is set to equal to K over M. omega squared is k over m. I get k to be 72, and m was 3 over 4. Yep. So the square root of that well, that came from the 24 and the 4, so let me go back to that. So that's 4 times 6 times 4. So that's 4 times the square root of 6. How about that? So the formula is this, that x of t is equal to c sub 1 times cosine omega t plus c sub 2 times sine omega t. Now, I want to say something about my philosophy. Sometimes people say that it's archaic. It is. It's an old method. And this method, if you look at how I do things compared to possibly what you see in physics, you have a lot of formulas in physics, a lot of memorization. I'm not remembering any formula. I'm just basically deriving just from what I'm given and just going from there. For me, 30 years from now, I'll be able to do this. But if it's a formula between now and 30 years, I'll forget the formula. So if I understand the process and where everything comes from, then you can always produce what you need. And so that's the strength of mathematics and studying the art of the mathematical process. So we have that. Replace the omega with 4 square root of 6. So x of t is c sub 1 cosine 4 square root of 6 t plus c sub 2 times sine of 4 square root of 6 t. Now we still have to solve for c sub 1 and c sub 2. Let's go back to the problem. Look at the next sentence. It says, initially the mass is released from rest from a point 3 inches above the equilibrium point. So if it's above, that denotes it's going to be negative, because at the equilibrium point, if gravity is pulling everything down, and if that downward motion is said to be positive, anything above that is going to be negative. So the negative sign just denotes the location of the initial start of this force based on the point of rest or the equilibrium position. So here, I'll write it here and then I'll write it down below. When we interpret this, the mass is released from rest. So here they're telling you that being released from rest, this is x prime of t is equal to 0. X, and here t is x prime of 0 is equal to 0. Right? And then the initial position, x of 0 is equal to negative 3 inches. So we have the initial velocity is coming from rest, so that's 0, and the initial position is negative 3 inches, since it says that it's above the equilibrium position. Okay? So let's go back down to the formula and see how that works in. Let's just put that here. X prime of 0 is equal to 0, and x of 0 is negative 3 inches. Negative 3 inches translated into feet, that's going to be what, 1/4 of a foot? So this is negative 1/4. Since the units there are in feet. So I take x of 0. I take this equation here. Just let t equal to 0 to work in this initial condition of x of 0 is equal to negative 1/4 of a foot. So x of 0 is equal to c sub 1 cosine, where if t is 0, then basically it's just cosine of 0 plus c sub 2 times sine of 0. That's said to equal negative 1/4. Well, cosine of 0 is 1, sine of 0 is 0, so this implies that c sub 1 times cosine of 0, which is 1, that's equal to negative 1/4. C sub 1 is equal to negative 1/4. So now, to work in the that second initial condition of x prime, we just take this formula, this equation that we have, and we just solve for x prime of t. So this is negative 4 square root of 6 c sub 1 times sine, just taking the derivative, 4 square root of 6 times t. So, you know, it's the derivative of the cosine, which is negative sine, and then you use the chain rule. The derivative of that 4 square root of 6 times t is just 4 times square root of 6. And that guy goes out in the front there. And then we move over, plus, take the derivative of this sine, so that's going to be cosine, and then the derivative of the inside would be 4 times the square root of 6. So this is 4 times the square root of 6 times c sub 2 times cosine 4 square root of 6 of t. Now we set x prime of 0 equal to 0. So x prime of 0. So, and if we understand we're dealing with cosines and sines, so definitely sine of 0 is going to go out. So let's look at the cosine. So that guy is 4 square root of 6 c sub 2. Cosine of 0 is 1. So that's equal to, according to this statement here, that's all equal to 0. So c sub 2 is equal to 0. So all I have operating is what's associated with c sub 1, because c sub 2 is 0. So we say conclusively that x of t is equal to the c sub 1, which is negative 1/4 times cosine 4 times the square root of 6 of t. And so this motion of this weight is associated there with a negative translation of cosine. Any questions there? Yes. That was number 13. Let me give you number 16 to do right now. Let me give you about 5 minutes, and see if I can find that one. There it is. Try your hand at that problem and see if you get it. I won't work it. I'll just put the answer, since it's even, I'll just put the answer up here in about 5 to 6 minutes, okay? Let me see if I can guide you along, just give you a couple of hints. The force that they give you, the force of 400 newtons, says it stretches a spring 2 meters. Well, they're begging you to use Hooke's law. So force is equal to some constant, the spring constant, times x. So here they give you 2 meters, that's going to be x, and then they give you 400 for the force. So they want you there to find k, the spring constant. So that's the first thing you see. And then the second sentence, a mass of 50 kilograms is attached to the end of the spring and is initially released from, well, let's just stop there. Let's just extract from that here that they give us this mass, and that's 50 kilograms. Right? Ultimately, they want you to find the equation of motion. So you understand that you're looking for this guy. That's what I'm looking for. So if I'm looking for that, I need omega. I need omega. So omega squared is K over M. Well, you got K and you got M. You see that? So it kind of feeds itself right into it, and you can get omega from omega squared. Now look at the initial conditions. Let me ask you about that. It says it's initially released from the equilibrium position with an upward velocity of 10 meters per second. Well, let me first ask this question. When it says it's released initially from the equilibrium position, they're saying, what's the initial position? 0. Very good. And then it says that the initial velocity is upward. So what does that say about 10 meters per second? It's negative. You got it. Okay. Well, you should be able to finish the rest of that. Those initial conditions are important, right? With the x of 0 equal to 0 and the x prime of 0 equal to negative 10. You find that derivative. Let me write the initial formula first. You have that, right? Then you find x prime of t. So that's going to be negative 2 c sub 1 sine 2t plus 2 c sub 2 cosine 2t. And then the initial condition is that this initial velocity is equal to negative 10. So t is 0, so that just gives you 2c sub 2. Cosine of 0 is 1, and that's equal to negative 10. That implies that c sub 2 is negative 5. With x of, it's just something you can kind of keep in your head. If, let me write it down here as a note. If you have x of 0 equal to 0, then that automatically implies that c sub 1 is going to be 0. Number 2, if x prime of 0 is equal to 0, then that would imply that c sub 2 will be 0. Just something you kind of keep in the future. Now, personally, I don't remember that because that's something to remember. So I just end up just working it out, just using the calculus. You know. Just look for the first derivative and go from there. Okay? Yep. Yep. And you go back up here, Dustin, that's the original equation there. And you just plug in your C1 and your C2. Yep. Okay. All right, I got 15 minutes. 15 minutes to cover 6.1. Okay, so it's 12. It's 12 o'clock, and there are 3 problems over there. 3 technical problems, not technical, but just technical problems that I have to work. Cauchy-Euler equation is section 6.1. Let's look at that.